Okay, we are doing, this is a study guide module 7 answer key review. And there was quite a few questions that we skipped. So we're just going to do the ones that I had you guys actually work on. Number 1, matching. So a force is a push or a pull that acts on an object. And I'm going to remind you, if you're following along, to be making your corrections in a different color. Please write that different color, up on the top of the page so that I know which one are your corrections for later on for grading. Friction is a force that results when a surface of an object rub against each other and opposes motion. Static friction. There was a typo. There was no definition for static friction. You had to write it in. Static friction is friction that opposes the initiation of motion. So remember, static friction is what keeps things still. It's what keeps things from not moving at all. Kinetic friction is friction that opposes motion once the motion has started. So static is what you have to overcome to get the motion to go. Kinetic is what opposes the motion once it's already going. Free fall, the motion of an object when it is falling solely under the influence of gravity. And inertia, the tendency of an object to resist a change in velocity. Oh, so there wasn't, well, there is a typo, but I just realized the definition we wrote in is actually printed right there without the gap. You guys see that? That looks silly. Anyway, number 2. All right, what is the height of a building in meters if it takes a dropped rock 4.1 seconds to fall from the roof? So what do we have? Time, 4.1 seconds. I'm going to remind you, you need to write all this down. You need to write it all out. What do you have? What do you know? What is your equation? Solve the equation. Okay? So what do you have? Time is 4.1 seconds. Acceleration, since it's asking for it in meters, are we going to use 9.8 or 32? Metric, 9.8. So acceleration is 9.8 meters per second squared. And what is the distance? So your formula is d equals 1/2 times acceleration times time squared. So we have 0.5 times 9.8 times 4.1 squared. When you work all that out, it comes out to be 82.4 meters. Number 3. A hot air balloonist drops a rock from his balloon. It takes 7 seconds for the rock to fall. What was the balloon's altitude in feet? So now instead of metric, we're doing English. What do you have? Time is 7 seconds. Acceleration, because it's in English, it's 32 feet per second squared. And what is its distance? Again, the formula, d equals 1/2 times a times time squared. So plug all that in, you end up with 0.5 times 32 times 7 squared, which 7 times 7 is 49. The answer is 784 feet. Before I move on to this page, I just want to give a quick shout out. Because yesterday's grading of the study guide, because yesterday's grading was simply a completion or not completion. You either did it on time. If you did it all but didn't do it on time, I just docked you 10 points, but you either got 100 for doing it or you didn't do it. So I didn't open up individual images. I just looked at your full pages so that I can see who attempted every question. And Alexis Wagenhauser, at a quick glance, I could see every step written for all of yours. So very well done with that. The answer for number 2 was 82.4 meters. All right. Number 4. State Newton's 3 laws of motion. Number 1, an object at rest or in motion will stay at rest or in motion unless acted upon by an outside force. Number 2, when an object is acted upon by an unbalanced force, the net force equals mass times acceleration. F equals ma. Alex, I'll come back to that question in a few minutes. And then the third law of motion is every action has an equal and opposite reaction. So those are Newton's 3 laws. Alex, really quickly, number 3 is 784 feet. You need to write all the steps down. Do not simply write the answer. Number 5. In space, there is almost no air. So there's virtually no friction. There's no molecules to rub up against. If an astronaut throws a ball in space with an initial velocity of 3.0 meters per second to the west, what would the ball's velocity be in a year? Assume there's no planets for it to run into. Guys, if there's absolutely no air and there's no friction, then there's no outside force acting on. This is going back to Newton's first law. So it would still be 3.0 meters per second west. There's no friction, there's no forces to slow it down. It's going to keep on keeping on until it runs into something. Number 6. A boy is running north with a beanbag in his hands. He passes a tree, and at the moment he's next to the tree, he drops the beanbag. Will the beanbag land next to the tree? And if not, will it be before or after? Will it be north or south? So he's running north and he drops it as he passes it. Is the beanbag going to be at it? Is it going to be south of it? Or is it going to be north of it? So the question is, where will it be? The answer is no, it's not going to be next to the tree. It's going to be north of the tree. It's going to keep its original velocity. It's going to continue past the tree in its initial velocity of traveling north as it drops through the air. So it's going to experience free fall and direction. So it's important to note that when something is traveling, it continues at its travel no matter what. Now, for question number 7, instead of the kid running holding the beanbag, there's a second kid. He's holding the beanbag. He's standing still, holding the beanbag next to the tree. And now the kid who's running just simply hits it as he passes. Now, is the beanbag going to be next to the tree or in front of or behind the tree? This time it's going to be, because its initial velocity was nothing. The object is going to follow the initial velocity. So this beanbag that gets dropped was not traveling. Instead, it was just staying still and got dropped. So it's going to stay right wherever it started, next to the tree. Number 8. A busy shopper driving down the road. Boxes are piled up in the back seat of the car. Evidence of the shopping activity. Suddenly, the shopper hits the brakes to avoid a collision. Hit the brakes so that they don't hit anything. Will the boxes get slammed farther back into the seat, or will they slam into the front seat where the driver can feel them, and why? Explain. It's going to slam into the front because it's matching the initial velocity. They were going forward, so they will continue to go forward until something stops them. In this case, the seat in front of it is what's going to stop it. Matching the initial velocity is your reason why. Number 9. When roads get wet, they get very slick. Obviously, the friction between the car's tires and the road decreases when the road is wet. But why? So the grooves in the road and in the tire, we'll say these are grooves, they are what create the friction. But when there's water on the road, the grooves are filled in. Less friction. Does everybody understand that? So the grooves get filled on both the road and the tires. So instead of having all these abrasive spaces to rub over, now the water's filled it and they're smooth because it's filled in the grooves. There's less friction. Number 10, in order to slide a refrigerator across the floor, a man has to exert an enormous amount of force. Once it's moving, however, the man may not need to exert nearly as much force to keep it moving. Why? How come you need more force to start it than you do to keep it going? Because those two forces that we're talking about, static force is overcoming initial motion. Kinetic force is once it's already moving. Of those two forces that we're talking about, static force is always greater. Getting it going and opposing the motion to begin with, that is greater than kinetic force. So your answer is static force is greater than kinetic force. Number 11, we skipped. There was quite a few actually that we skipped. So I am going to go ahead and turn to page. We did number 12. So number 12, a father is trying to teach his child to ice skate. I bet you that's fun. As the child stands still, the dad pushes him forward with the acceleration of 2.0 meters per second squared north. If the child's mass is 20 kilograms, what's the force with which the father is pushing? Since they're on ice, you can assume and ignore, there's no friction, okay? So what do we have? Once again, step by step. Step one, what do we have? Mass, 20 kilograms. Acceleration, 2.0 meters per second squared south. Force is what we're looking for in newtons. So what's your equation? Force equals mass times acceleration. In this case, our mass is 20. Our acceleration is 2.0 meters per squared south. So the answer is going to be 40 newtons. But what's the direction? So in this case, it's going to be north. It's the opposite. I'm not worried about you knowing the direction. If you're still struggling with that part, that's okay. But as long as you know how to plug in the equation and get to the answer, I'm okay with that. So it's going to be 40 newtons north. I'm going to pause for just a quick second. Module 7. Okay. Since we're ignoring friction, the only force involved is the force that the dad exerts. So the total net force is equal to the dad's force. Since the child is accelerating north, the father has to push with the force of north. Got it? That's the explanation that your book gives. Okay, moving on. Number 13. The Mars Exploration Rover, MERA, M-E-R-A, landed on Mars in 2004 to explore and take pictures and sample all the rocks in the soil. If MERA has a mass, write it down, of 185 kilograms, and the acceleration due to gravity on Mars is 3.7 meters per second squared, so that would be G, 3.7 meters per second squared. What is the weight of MERA on Earth and Mars? 2 parts, guys. Now, you have to answer this. You have to have 2 answers, one for Mars and one for Earth. Well, it gave us acceleration due to gravity on Mars, so our G is going to say 3.7. But on Earth, the acceleration due to gravity is going to be what? In this case, is it metric or English? It's metric. It gave us kilograms as the mass. So you're going to use 9.8. So you're going to answer this twice. Mass, 185 kilograms. Gravity, 9.8 meters per second. And gravity, 3.7 meters per second. And you're looking for weight. And the formula that you're going to use, the equation you're going to use, is weight equals mass times gravity, m times g. So 185 times 9.8 is 1,813 newtons. And 185 times 3.7 on Mars is 684.5 newtons. 684.5 newtons. So there was, actually, I think it should be 685.5. I think I did my math wrong. 685.5 newtons. So you should have 2 answers. We skipped 14. We skipped 15, 16, and 17. So keep changing in your book to number 18. All right, a child pushes against a large doghouse, trying to move it. The doghouse remains unmoved. It doesn't move. The kid's pushing, it does not move. What exerts an equal and opposite force, Newton's third law of motion, in response to this child's push? Okay, so Newton's third law, it's going to have an equal and opposite reaction. So if the child is pushing on the doghouse, the question says, what exerts the equal and opposite force in response to that push? What is the force exerted on? The equal and opposite force, so there's two parts. The equal and opposite force is exerted by the doghouse onto the child. So what is exerting the force and what is that force being exerted onto? Two parts. It's being exerted by the doghouse onto the child. Number 19. A man leaning up against the wall with a force of 20 newtons to the east. So what is that force exerted on? What is the force exerted by the wall onto the man? Equal and opposite. So if it's 20 newtons east, the answer is going to be equal, 20 newtons, and opposite, west. So the answer is 20 newtons west. And number 20, the last one, name the 4 fundamental forces in creation. What is the weakest fundamental and what is the strongest? So name all 4, and then what's the weakest and what is the strongest? So all 4, electromagnetic, strong nuclear, weak nuclear, gravitational. Those are the 4 forces. The strongest is strong nuclear. The weakest is gravitational. All right, I am going to stop recording.